Okay, hello everyone. Now, last video or lecture we have been discussed in detail about Fourier sine and cosine transform and its corresponding numericals. In this video, we are going to discuss properties of Fourier transform. So let's start. So this is the first property, that is called as your linear property. Okay, it states that if f1 omega capital F1, okay, capital F1 omega and capital F2 omega are Fourier transforms of small f1x and f2x respectively, then Fourier transform of linear combination of these two functions, that means a constant a multiplied with this function plus another constant b multiplied with this function f2x, will be equal to a into f1 omega capital F1 omega plus b f2 omega. So this is the statement. Here we are going to go for the proof of this property. Okay, in your exam straightly this property asking that you have to state and prove the linear property of Fourier transform for 2 and 3 mark. Okay, here is the proof. Very simple. We know in general Fourier transform of function small f1x can be written as f1 capital F1 omega, which will be in the integral form as 1 by 2 pi root over minus infinity to plus infinity small f1x e to the I omega x dx. That we know. Simple. Okay. Similarly, Fourier transform of small f2x is your capital F2 omega will be equal to 1 by 2 pi root over minus infinity to plus infinity f2x e to the I omega x dx. So here x transformed to omega, x transformed to omega, but this is your f2 and f1x. This is your f1x, f2x. Okay, now we are going to just add. Now we are going to consider, see, Fourier transform of a f1x plus b f2x. Here this is your Fourier transform. Okay, if we are going to consider Fourier transform f dot t, if we are going to consider Fourier transform of a multiplied with f1x, b another constant multiplied with f2x, then what we can write, that is your 1 by 2 pi root over minus infinity to plus infinity, this entire function, that is your a f1x plus b f2x into e to the I omega x dx, which will be equal to, a is the constant taken outside, this integration can be written as this integration. Here is the plus, so I can segregate this integration by two integrations, like 1 by 2 pi root over minus infinity plus infinity f1x into the e to the I omega x dx. Another integration is this one, that is your f2x e to the I omega x dx. So here this one, this integral is nothing but your capital F1 omega, this integral is nothing but capital F2 omega, just substituted and proved. So Fourier transform, this is your Fourier transform f dot t. Okay, f dot t, Fourier transform of this one here is this one has been proved. Now we are going to go for the second property, that is your change of scale property. This is very much important for your exam. If f omega is the Fourier transform of a function fx, then Fourier transform of f(ax) will be equal to 1 by a capital F of omega by a. Here a is any arbitrary constant. Here a is a constant. Okay, so this much we have to prove. Very simple. We know Fourier transform of a function f of x, or that is your f omega, equal to 1 by 2 pi root over minus infinity to plus infinity by fx e to the I omega x dx. So if we are going to consider function is your f(ax), so instead of fx we have to write f(ax) into e to the I omega x dx. So Fourier transform f(ax) will be this much we have to write. Now we are going to substitute ax equal to t. That means dx will be equal to dt by a, and here limit is not going to be changed. Here if I will put minus infinity, x equal to minus infinity will be minus infinity, and x equal to infinity, here t also will be infinity. Limit is not going to be changed. So here f of t f(ax) can be written as f of t, Fourier transform of ft, because we considered ax equal to t. So f of t equal to 1 by 2 pi root over minus infinity to plus infinity. This will be f of t into e to the power I omega instead of x. Here ax equal to t, so x equal to t by a. So instead of x we have to write t by a into dx. Dx will be dt by a, right? Now here you can see a is a constant taken outside, right? And this t by a here can be written as omega by a. So Fourier transform of f of x equal to Fourier transform of f of t will be equal to a is your constant taken outside 1 by a 1 by 2 pi root over minus infinity to plus infinity f of t e to the power omega by a. We can write omega by a t dt, right? Now here this integral can be written as capital F of omega by a. Why? Because we know that suppose Fourier transform of f of t we are going to consider Fourier transform of f of t, then what we have to write? 0 to infinity 1 by 2 pi root over 0 to infinity e to the I omega x dx, which will be equal to f of omega. So instead of omega, if it will be omega by a, then it will be written as f omega by a. Okay, or you can think in this way that if we are going to integrate this integration with respect to t, then we have to substitute the limiting value at t. So omega by a will be constant, at the end omega by a will be there. So finally we can found a function which will be the function of omega by a. Okay, so here this property has been proved that Fourier transform of f small f x will be equal to 1 by a capital F of omega by a, hence proved. Okay, now we are going to go for the third property, that is your shifting property. So according to this property, Fourier transform of f of x minus a will be equal to e to the power I omega a f of omega. Here a is a constant. Here a is a constant, any arbitrary constant. Okay. How we are going to prove it? We know in general Fourier transform of any arbitrary function which is in the domain x, small x, and transformed to omega can be written as f dot t f of x or capital F of omega equal to 1 by 2 pi root over minus infinity plus infinity. This same function, that is your f of x e to the I omega x dx, that we know. Now instead of f of x we substituted as f x minus a. Here a is any arbitrary constant, can be written as 1 by 2 pi root over minus infinity to plus infinity. Instead of f of x we have to write f x minus a into e to the I omega x into dx. Here we have been substituted, instead of x minus a equal to t, then x will be equal to t plus a, dx will be equal to dt, and limit is not going to be changed. How? If I am going to substitute, instead of x equal to minus infinity, t also will be minus infinity, because this is a small constant as compared with infinity, t will be infinite, minus infinite. If I will be substitute x equal to infinite, t also will be infinite, so limit is not going to be changed. I written also here. So above equation, that means this equation will be Fourier transform f dot t of f of x minus a, because can be written as f of t, because t equal to x minus a we have been considered 1 by 2 pi root over minus infinity plus infinity. This will be written as f of t e to the I omega. Instead of x it will be written as t plus a into dt, because dx will be equal to dt. So here you can see this, in this term we can get two terms, e to the I omega t into e to the I omega a, but this integration with respect to dt, so e to the power I omega a will be a constant, can be taken outside of this integration. So I done same thing, e to the I omega a I taken outside, and here I forget to write 1 by 2 pi root over 1 by 2 pi root over into minus infinity to plus infinity f of t e to the I omega t dt. This integration is nothing but called as Fourier transform of f of t or capital F of omega. So hence we found Fourier transform of f of t equal to e to the I omega a into this integration can be written as capital F of omega. And instead of t, again I substituted value x minus a. So Fourier transform of f of x minus a will be equal to e to the I omega a into f of omega has been proved. This property also very important, asked in your exam 2 to 3 marks. Practice it for your exam. Okay, next we are going to go for modulation theorem or property. This is also another important question. Directly it will ask that state and prove modulation theorem or modulation property regarding Fourier transform. What is that? If f omega, capital F omega, is the Fourier transform of a function f of x which is in x domain, then Fourier transform, this is Fourier transform f dot t, then Fourier transform of fx into cos ax will be equal to 1 by 2 whole into capital F of omega plus a plus capital F of omega minus a. Okay, this much we have to prove. Most important property or theorem, 2 to 3 mark you can found, always you can found in your exam. Okay, now how we are going to prove it? We know Fourier transform of a arbitrary function f of x or capital F omega can be written as 1 by is written as 1 by 2 pi root over minus into plus infinitive f of x into e to the I omega x dx, right? So instead of f of x, we consider that f of x into cos ax. So hence right hand side will be 1 by 2 pi root over minus infinity to plus infinity. Instead of fx, we have to write fx into cos ax into e to the I omega x dx, right? This will be 1 by 2 pi root over, integration will be minus infinity to plus infinity, f of x cos ax can be written as e to the I ax plus e to the minus I ax by 2 into e to the I omega x dx, right? So here this integral can be segregated into two integrals because here is a plus sign. So what are the integrals? Here you can see this 2 is constant taken outside of the integration, 1 by 2 whole into, this is 1 by root over of 2 pi, 1 by 2 pi root over minus infinity to plus infinity, this one fx multiplied with this one and this term also, e to the I ax into e to the I omega x dx. Got it? Plus 1 by 2 pi root over minus infinity to plus infinity integration fx, this one e to the power minus I ax into e to the I omega x dx. Okay, so here 1 by 2 already is there, 1 by 2 pi root over minus infinity to plus infinity f of x into e to the I, here e to the ax e to the omega x can be written as e to the I omega plus ax dx. Likewise here it can be written as e to the I omega minus ax dx. So here you can see Fourier transform, that implies Fourier transform of f of x cos ax will be equal to this integral. What we can write? Instead of omega, it is written as omega plus a. Okay, we know that Fourier transform of a function is written as f of omega when it will be like this, minus infinity to plus infinity f of x into e to the power I omega x dx. So instead of omega, suppose s is there, so this will be written as f of s. Instead of omega, k will be there, so this will be written as capital F of k. I discussed these things in our first video where I discussed the basics of Fourier transform. Okay, if instead of omega, omega plus a will be there, so it will be written as capital F of omega plus a. If it will be omega minus a, it will be written omega minus a, f of omega minus a. Same thing here, I written that this integral will be written as capital F of omega plus a. This integral will be written as capital F of omega minus a, hence proved. This is one of the important property or theorem you have to remember, practice for your exam. The next property is your fifth one, derivative of a Fourier transform. So according to this property, if f omega is the Fourier transform of f of t, small f of t, then nth derivative with respect to omega of capital F of omega will be equal to I to the power n Fourier transform of t to the power n into f of t. How we can prove it? It is very easy. Here you can see, in general, Fourier transform of f of t or capital F of omega is written as 1 by 2 pi root over minus infinity to plus infinity f of t to the I omega t dt. Let this is your equation number 1. Now we are going to differentiate this equation number 1 both sides with respect to omega. So in your left LHS of this equation number 1, we have to differentiate with respect to omega. So d by d omega of this capital F of omega will be equal to, here if I will differentiate this one, here f of t will be act as constant, only here e to the I omega t is there. So if I will differentiate with respect to omega, then the value will be it into e to the I omega t. So I taken outside, t I written over here because this integration is integrated with respect to t. So a t I could not take outside. Here you can see differentiation of e to the power I omega t with respect to omega. E to the I omega t with respect to omega means how much? Will be I t omega. So t will be constant, it into e to the I omega t. But t is not constant here for the integration. If I am going to consider integration, t I could not take outside, but I taken outside 1 by 2 pi root over minus infinity plus infinity t into f of t e to the I omega t dt. Now second time if I will do the derivative both the side, so it will be d2 by d omega 2 of capital F of omega, and derivative of this one will be again it e to the I omega t. It means I will be multiplied with this one, it will be I square and this will be t square. Second time derivative I found I square t square. Third time I cube t cube. Nth. Hence considering nth derivative of equation number 1 with respect to omega, what we can found? Nth derivative of this one, dn by d omega n of capital F of omega will be equal to I to the power n 1 by 2 pi root over minus infinity to plus infinity t to the power n f of t e to the I omega t dt. So here you can see that this is nothing but this integration. This integration is nothing but your Fourier transform of this function. So we can write this one as I to the power n into Fourier transform of this one. Here I have to write that this is Fourier transform. Okay, f dot t, Fourier transform of this function, that is your t to the power n f of t. And here this also can be written as, here what we found nth derivative with respect to omega of capital F of omega is equal to Fourier transform of I to the power n is there, I to the power n Fourier transform of t to the power n f of t. This much we found, right? So this one will be a Fourier transform of t to the n f of t will be equal to 1 by this I to the power n will be moved this side, means this will be 1 by I to the power n dn by d omega n of capital F of omega, or Fourier transform of t to the n f of t will be equal to this 1 by I to the n can be written as minus I to the power n dn by d omega n of capital F omega. Okay, either you have to remember this one or you have to remember this one. Using this property, what type of question you can face in your exam, here I am going to explain. Just watch. Suppose a arbitrary function f of t and its Fourier transform, suppose it has been given that omega square by 4. Suppose a arbitrary function, in the question it will ask that if Fourier transform of f of t, a unknown function f of t, is your omega square by 4, then t square f of t, Fourier transform of t square f of t will be how much? It has been asked. Here you can see Fourier transform of t to the power n f of t is your minus I to the power n nth derivative. If it will n equal to 2, then this will be I to the minus I to the power 2, and this is the double derivative of f of omega. So in the question itself it has been given that Fourier transform of f of t is this one, or this is nothing but capital omega. Okay, so this answer will be how much? Iota to the power 2 double derivative with respect to omega of capital F omega, that is your omega square by 4. So what will the answer? Iota to the power 2 minus I to the power 2, first derivative will be 1 by 4 is constant. First derivative means it will be 2 omega, then d by d omega we have to consider, then second derivative we have to consider minus I square, 1 by 4 is there, second derivative 2, second derivative 1. So here this minus I square means minus 1, and this is 1 by 2. So finally we can get the answer minus 1 by 2. So this type of question, short question, you can found based upon this property. Okay. Next we are going to go for our sixth property, that is your Fourier transform of a derivative. Last one, fifth one is your derivative of Fourier transform. This one is your Fourier transform of a derivative. According to this property, Fourier transform of fnt means nth derivative of a function f of t, and its corresponding Fourier transform will be equal to I omega minus I omega to the power n Fourier transform of f of t. Okay, or we can write Fourier transform of nth derivative of a function is equal to minus iota omega to the power n into capital F of omega. Let's first prove it, then what type of question you can face based upon this property that we are going to discuss. We know if we have a function f of t, its Fourier transform or capital F of omega will be written in this format, in this integral, in the form of this integral, that is your 1 by 2 pi root over minus infinity plus infinity f of t to the I omega t dt. Now consider f dash t, that is your first derivative of this function small f of t. Consider Fourier transform of this one. Fourier transform of f dash t will be written as can be written by in the form of integral, that 1 by 2 pi root over instead of f of t we have to write f dash t e to the I omega t dt. So here this is your first function e to the I omega t, this is your second function. So we are going to consider the by parts. Here this one is your first function, this one is your second function. As it is unknown, so we consider that this is your second function. So considering the by parts, integration by parts, we can write the first function integration of the second function minus integration minus infinity to plus infinity derivative of the first function with respect to t integration of the second function. Okay, here integration of the second function will be equal to ft, because here derivative with respect to t integration, that means one derivative will be cancelled. So we found ft. What will be the limit is a minus infinity to plus infinity, minus here derivative of first function will be with respect to t will be I omega e to the I omega t. I omega e to the I omega t is there, and integration of f dash t, that means here f dash means first derivative of ft with respect to t, integration with respect to t. So the one derivative will be cancelled out, so we can found ft and e to the I omega t dt, integration minus infinity to plus infinity. We know if ft is a continuous and differentiable physical observable quantity, then ft 0 for t plus or minus infinity. What is the meaning of that? Here simply you just consider this is signal. Suppose this is a signal propagating from a transmitting antenna. Suppose this is the antenna and a signal is propagating along x-axis. Okay, so if it is so, it can be represented by f of t, suppose, and this f of t value will be how much? You just think will be how much if we are going to consider at the infinite distance. At the infinite distance, the signal will be reduced or it will be attenuated, its amplitude will decreases, and at infinite this signal is going to be 0. So at t will be infinite, either this side, suppose at origin a tower is there along x-axis up to positive infinite, along negative x-axis if I am going to consider up to minus infinite, at plus infinite ft will be 0, at minus infinite ft also will be 0. So here this signal is a differentiable and continuous, a sinusoidal wave function, you just consider as an example. So here same thing I have been written, that we know f of t, if a function is a continuous and differentiable, then this value will be equal to 0, or the function could not be found at t equal to plus or minus infinity. You just remember this condition is most important condition when you are going to go when you are going to study the quantum mechanics in your 5th semester. This condition is very much essential at that time, that function could not be found at plus and minus infinite. Okay, you just remember this one. So if it is so, if I will put instead of t infinite or minus infinite, this value f of t will be 0, so this term will be 0. Got it? Only we can get the second term. So second term will be equal to how much here? Left hand side is your f of t f dash t, that implies Fourier transform of f dash t will be equal to here minus I omega is there taken outside, minus infinity to plus infinity f of t e to the I omega t dt. Or we can write this is, sorry, here I forgot to write 1 by 2 pi root over, 1 by 2 pi root over is there, 1 by 2 pi root over. So if it is so, then this integral is nothing but your Fourier transform of f of t. Now similarly, if you are going to consider Fourier transform of double dash f double dash t, Fourier transform of double dash t, then similarly you can found minus I omega to the power 2, minus I omega to the power 2 Fourier transform of the original function. Okay, likewise if we are going to consider this way, then nth derivative and its corresponding Fourier transform of nth derivative of a function will be equal to minus I omega to the power n Fourier transform of that original function, that is your f of t, or this can be written as capital F of omega. So what type of question you can face in your exam? 1 or 2 mark, 1 mark multiple choice questions or short questions based upon this property. Here I am going to do for you one example, that suppose Fourier transform of a arbitrary function. Same example I am going to take what I considered previously for the property number 5 that I am going to consider here. Suppose any arbitrary function is there. Okay, arbitrary function is there, f of t, and it's f of Fourier transform of that function, that is your f of omega, is given as omega square by 4. Suppose omega square by 4 has been given. You have to find out what will be its Fourier transform, what will be its Fourier transform of f f double dash t. Suppose f double dash t, what is the Fourier transform? If Fourier transform of a function f of t equal to this much, then double derivative of this function and its corresponding Fourier transform will be how much? Direct you have to use this one, this expression. So here n equal to how much? 2. So the answer will be how much? Here you can say the answer will be equal to minus I omega here, considering this expression, minus I omega square into Fourier transform of f of t, what given in the question is your omega square by 4, right? So here minus I square is your minus 1, omega square by 4. So we found finally omega minus omega to the power 4 by 4, direct answer. Okay, this type of question you found in your exam, short question. Okay, this is all about the basic 6 properties of Fourier transform. You go through that. All the properties are important for 2 to 3 marks. Based upon these properties, you can find short questions in your exam. So finally, if you like this video, please do subscribe and share with your friends. Thank you so much for watching this video. In our next class, we are going to discuss Fourier sine and cosine transform of derivatives. Okay, so thank you so much for watching this video. Thank you.